How's it going, everyone? This is Strophium, and I'm going to do some basic C++ tutorials. And I figured I would do some C++ tutorials, particularly because a lot of new programmers and programmers that use languages like C# and Java, maybe even like Python, higher level languages, they can be very intimidated when they try to approach C++, and for that reason, they tend to put it on the back burner a lot, and they miss out on a lot of opportunities to learn some more fundamental aspects of programming that C++ really helps you understand. So I thought what I would address today is the concept of pointers. C# and Java and other languages like that, they use pointers and references under the hood very readily, but they occlude that from your vision. And I think understanding how memory works helps you be a better programmer in all languages, even languages that don't force you to worry about things like that. So we're going to get into the ideas of what pointers are, how they can be used, and we're going to try to just eliminate all of the scary aspects of pointers, because I remember when I was first learning C++, pointers scared the crap out of me, and there's really no reason to be afraid of them. You just have to be diligent about how you manage your memory. So let's start with the basics. What is a pointer? Well, a pointer, as its name implies, is a data type that points to something. So if you declare an integer and you instantiate an integer and you have an integer value stored in a variable, that variable has an address in memory somewhere. It's got a physical location that the processor needs to access in order to manipulate it. What a pointer does is it stores specific memory locations based off of the type that it's intended to point to. And this can be really useful because if you have large data types or you have large aggregates of data types and data that belongs in a particular class, but you want to reference it somewhere else, you can use pointers and you don't have to copy a lot of this data, which is really, really handy. So we went over basically what a pointer is, what an address is. So what does that look like in C++? If I said I wanted an integer called foo, and I want to set it equal to 5, I can cout foo, and I will get just the value of foo, which is 5, printed out. So here's where it gets interesting. How do I know where this was allocated in memory? And the way I can check that is the address operator. If you put an ampersand behind a value, what you're really saying is give me the address of this. So we have foo, and I want to print out the address of foo. I don't care what it has, I care where it is. So when we print this out, we get a hexadecimal value. This is in OODAF 888, which is somewhere on the stack. And the reason I know it's the stack is because I have a stack allocated value. So main is a method, just like any other method, and foo is declared locally on it. So I know that foo will be allocated on the stack because I'm not requesting for it to specifically be allocated somewhere else. And there's two main regions of memory. There's really three, but there's two that you have to be concerned with. And there's the stack, which is a limited, it's pretty large, but it's still limited, section of memory that's intended for quick use and quick clearing. So when you enter a method, you can stack allocate variables that can be used locally in that method, and then when that method ends, it wipes off that chunk of the stack. So once I exit main, assuming this was a different method other than main and the program didn't terminate, everything that I declared in here would no longer be accessible in memory. It would be garbage. Additionally, you can declare, say I wanted to dynamically allocate on the heap and have a value persist outside of those methods. I could declare an integer out here, and I would only be able to access it by its memory location. So I need to declare it as an int pointer. And then I would instantiate it here by saying bar equals new int, and then I could pass it a value like that. And the problem here now is if I cout bar, a naive programmer might think that I'm printing out the value of bar. But if we look up here, its type is not of integer, its type is of int pointer. So when I print out its value, what I'm going to get out of it is an address. So see, we get a heap address now. And I can't tell that just by looking at it, I can tell by knowing how I allocated it. This is a heap address of where bar is located. It's the same thing as doing a cout of the address of foo. These both yield address values. So this is where these values are located. So how do we get the value out of a pointer? We have to dereference it. And conveniently, or I guess confusingly, depending on how you think about it, C++ uses the star both as the pointer declaration and as the dereference operator. So if we put an asterisk behind our value, just like we put an ampersand behind the value to get the address, we put the asterisk behind a pointer to get the value. So we're cout star bar end line. So the last value that we get here should be the value of bar, which is 10. That's correct. And it's similarly, we can just print out foo normally. Okay. So you can see how variables and pointers, they kind of have an inverse relation where you need to use an operation to get the address of a variable, and you need to use an operation to get the value of an address, value of a pointer. Whereas printing out the raw values gives you those raw values. Something to be noted now, though, is, like I said, when we hit this bracket here, this brace, foo will be deallocated manually. We don't have to worry about that. But we manually allocated memory for bar here, which means once we get out of here, our program ended, and we never said we were done with this memory, which leaking at the end of an application isn't a huge deal, but you can leak within methods of an application, and you could lose the reference to the variable altogether, and then you just can't deallocate it ever. And that's what's called a memory leak. When you allocate memory and then you have no way of removing it anymore, you have leaked memory, which means that you're using up resources that you cannot and will not ever clean up. The cleaning up of resources is really, really simple. You just say delete bar, and now bar, I believe, is null pointer. So if we printed out bar here, we should see, okay, we're getting the addresses of two values, we're getting the values of two values, and then we're printing out what bar is. Okay, it's just garbage. It's not null pointer, but it's just garbage. If we try to dereference it, then bad stuff probably happens. And I think this is actually undefined behavior because it's pointing to garbage. Yep. Exception thrown, read access violation. So we're trying to dereference an address that we don't own. And that's when you get exceptions. So the moral of the story is allocating memory for something is not bad. It just determines where it's going to exist, how long it's going to exist, and how we have to operate on it to get meaningful values out of it. Additionally, size becomes a huge issue. So if I have a larger data type than an integer is just 4 bytes, and an int pointer is also 4 bytes. So we don't get any size trade-off by using a pointer rather than the data type itself. Okay. But say we're using something like a string. Yeah. String foo. And then we declare foo. Oh my goodness. So we've declared a foo pointer, and we've instantiated it on the heap. Additionally, we could say string bar hello bar. Let's do hello foo here. Okay, so these are both variables that have different lifespans. Bar is going to be manually cleaned up, whereas foo we're going to have to delete. In fact, let's just do it here. Just for good practice. Every time you do a new, you want to do a delete. Here's an interesting thing that we could try to do. Cout size of foo, cout size of bar. Look at this. So the size of foo is 4 bytes, like I said, because what we're really storing is an integer value, and that's an integer value of the address of where foo actually is. Whereas bar got 28 bytes. That's a big old variable. Imagine now if we had thousands of strings, and this is very common in larger applications where you get very large aggregates of data. And if something is 9 times heavier by using its raw data type, it becomes a lot more performant to move it around if you're just using pointers to it. And I believe actually strings get larger based off of the memory you put in them. Nope. Maybe you just need like a lot of stuff in them. Nope. Strings are pretty consistently 28 bytes apparently. And I believe that might be because strings are doing some dynamic allocation under the hood as well. I'm not entirely sure, but that makes sense. Because what strings are really are arrays that can dynamically resize themselves, and the only way you can do dynamic resizing of arrays is if you're doing heap allocation in some way or another. So that's interesting. We learned a thing. But yeah, so relating this to something larger scale like game applications, you might have entities that have tons of data that they're storing that might not be relevant at any given time. And you might also want, for example, if you have subclasses, something that you can do with pointers is you can store generic entity pointers, and within that you can have enemies, you can have allies, you can have wizards, rogues, all these different specifications, and they can all be classified under entities. So what you can do is you could have like an aggregate of some form, whether it's like a hash map or a vector or even just a regular old array of entity pointers. You can iterate through them very fast because they're all the exact same size, they're all the exact same type as far as you're concerned, and you can operate very efficiently on data that way. So that's pretty much the long and the short of what pointers are. You shouldn't be afraid to use them. You should really understand when pointers are good, when they're necessary, and just not be afraid of them. Additionally, there is something in C++ called a reference, which a lot of languages have. In fact, languages like Java or C#, which I keep going back to, they use references under the hood all the time. So, for example, say I wanted a method that void do thing, and what I could do is I could take an int reference value for that thing, do thing with reference, void do thing with pointer. Bear with me for 1 second. and void do thing with copy. These are three ways that you can pass data to methods in C++. You can pass by reference, you can pass by pointer, or you can pass by copy. And when you pass by a reference, what you're really doing is you're just saying, here's the object, don't bother copying it, don't bother passing a pointer, just operate directly on this and I trust you not to ruin it. Passing by pointer is saying, here is the memory location of my thing, do with it as you please. I'm still going to own it, but here's the memory location of where it is. So I'm going to trust that you won't ruin it. Passing by copy is totally safe, and it just creates a carbon copy of value at the point of calling the method, and then it just lets you operate on it, and you can hack it up, do whatever you want, and ruin it, and the calling code does not care. So just demonstrating what these methods are going to do is, say I want to declare int foo equals 5. And I want to call by reference, do thing with reference foo, and then I want to see out foo. So here, if I do value plus plus, let's just do that for all of these. So no matter what we're doing, we are passing in the value and then incrementing it. For the pointer, we're going to have to dereference it and then increment it, because if we just increment the pointer, we're going to actually corrupt the data. So all of these, what they're doing is they're just grabbing that value that they get and they're incrementing it. So doing that by reference, we pass in a value of 5, increment it, and then now foo is going to have the value of 6. If you don't believe me, we're going to print it out now. See, we get 6. And that's because we're passed a reference to foo rather than a copy. And the default is a copy. We can see now, if we pass a copy, we're incrementing that copy, but the original remains unchanged. We have the value of 5 here. If we pass by pointer, notice that we get a compilation error now. Argument of type int is incompatible with type int pointer. So what we have to do is pass the address of foo, so that way we're passing in an int pointer. And now what's going to happen is we pass in the address of foo, we then dereference that address to get back to the reference, and then we increment that reference. And we get 6. The reason being is because we're not doing any copying. We're passing in the address and then operating directly on that. So the original value gets corrupted. So there's a lot of different reasons and use cases where you would want to have different combinations of these. And there's ways that you could make references safer. So passing back copy is 100% safe. You never ever have to worry about that. The thing that becomes a problem when you're dealing with large complex sections of code is that if you're passing large data types and you're copying them every time, it becomes very, very non-performant. So the use case comes up where we would really want to pass by reference if we could, but we don't want the danger of corrupting our code. The way that we can get around this is by passing a const reference. And constness in C++ precludes you from modifying the value. So notice that we get a compilation error here. So when we're modifying value, we're saying expression must be a modifiable L value. So by making this a const reference, it allows us to work with data in a very performant way, and the compiler will catch any kind of dangerous stuff that we're trying to do. Whereas, if we don't care about that and we actually want to use this as a mutator type of method, then we can just pass by reference. Passing by pointers and passing by references are functionally the same thing, because what you're doing at the end of the day is you're modifying memory directly. But these two, it's just a syntactic sugar difference. It's a stylistic difference. Whichever you're probably taught within school is probably what you would do more often than not with the other. The difference, the big difference between these two usages is that when you pass by reference as a parameter argument, references can never be null. So if you want to make sure that you're never operating on a null pointer, then you want to set your argument as a reference. If you want to allow null pointers and check for null, then you want to pass by pointer. And that's really the big difference, is that you, with my own personal code, I design it, if I'm ever operating on a value and I don't want to copy it, then I default to a reference. And then I ask myself, do I ever want this to be null? And if the answer is yes, it might be null, then I need to use a pointer. So default to copy. If it's a large data type, you want to use a reference. If it needs to be null, you want to use a pointer. That's a good frame of logic to keep in mind. Just to show you, for example, I could say int star foo equals new int 5. And if I wanted to pass by reference, I could dereference that heap allocated value and pass it by reference, and this works. Notice if I try to pass a pointer to a reference, it doesn't work because they're not matching types. Here's a weird thing. So foo is a null pointer, and I want to pass value of foo here. This will not actually it won't actually run. Notice see, we get exceptions because we're passing in values that can't take null pointer. Actually, it might be a little bit more clear if I just do it this way. Notice how non-const L value reference of type int cannot bind to R value of type std null pointer. So like I said, references can't be null, so we can't pass anything that dereferences to null pointer to the method. Whereas this works just fine. Okay, excellent. All right, so that's the basics of pointers and memory in general, and the similarities and differences between pointers and references. I hope it was educational for you guys, and feel free to like and subscribe.